Hi, it's Moser with a quick tutorial on periodic trends in atomic radii and reactivity. After you've watched this video, you should be able to correctly define atomic radius, use periodic trends in atomic radii to arrange the elements in order, either increasing or decreasing of atomic radius, and explain the basis of these trends, as well as how those relate to the trends that are seen in reactivity. So you already need to know what valence electrons are. You need to already know how to determine the number of valence electrons from location on the periodic table, and it would be really helpful to know the difference between metals and nonmetals too. Hey, remember these? We've got the Bohr ring, the Bohr planetary model, the early quantum model, and we've got the modern quantum atom. So we know that both of these models bring their own thing to the table. That said, we're going to use the Bohr model to talk about atomic radius because it's simpler to understand. But I want you to keep in mind, this is still closer to reality in terms of what an atom is. A little tiny positive BB in a giant room full of cotton candy. Okay, with that out of the way, when we look at two identical atoms that are covalently bonded, that are sharing electrons, we can look and measure the distance between their nuclei. Okay, well, great. If we look at 1/2 of that distance, that is the radius of that atom. Oh, so 1/2 the distance between the nuclei of identical bonded atoms, that's an atomic radius? You got it. Now, that's not so interesting, and obviously we're not measuring this with little calipers or anything. What's interesting is that if we look at the periodic table, because remember, this is all about the periodic table, we see that atomic radii decrease as we go from group 1 to group 18, and generally increase going down a group. Wait a minute. So you're saying, you got your periodic table out, right? That as we go from group 1 to group 2, group 3, group 4, all the way over to group 18, even though we're adding electrons, the atoms are getting smaller? What? Does this give you any sort of deep trouble in your soul? Yeah, I thought so. So here I've drawn the elements of the second period, starting with lithium, moving through beryllium and boron, carbon, nitrogen, oxygen, fluorine, and of course finishing up with neon. And I've drawn them getting smaller. Their atomic radius is decreasing. But we want to understand why. So you have to remember that every atom is a tug of war. We have a positively charged nucleus and negatively charged electrons out in those big fuzzy clouds all around it, the orbitals, even though we've drawn them here as sort of Bohr planetary orbits. Remember reality. And that nucleus is exerting an attractive force on the electrons because they're oppositely charged. Each proton in the nucleus exerts a charge on each electron that's out in the orbitals. So in this case, we have 3 protons exerting force on 3 electrons. Now, 2 of those electrons are fairly close. They're in the lowest main energy level. They're in the 1s subshell. But one of them is a little further away. It's a little harder to keep a grip on. Perhaps you've known a family with 3 kids and the baby gets away with everything. Well, it's a little harder to get a grip on that one that's a little further out. Okay, so what happens when we add protons and we add electrons? Well, here we've gone to boron. So we now have not 3 protons, but 5 protons pulling on 5 electrons. Well, we're just generating more force in general. But in addition to that, we've still got those 2 inner shells sitting in the 1s. But there are now 3 electrons in the uppermost occupied energy level. Sort of more points to get a grip. Because there are more protons exerting a force on more electrons, and there are more electrons in that uppermost occupied main energy level, here, the nucleus is actually able to exert a stronger pull on the outer shell and pull it in just a little bit tighter. So let's skip down to nitrogen. So in nitrogen, we now have 7 protons pulling on 7 electrons, and 5 of those electrons are in the uppermost occupied main energy level. That's a lot of places to get a good grip on that outer shell, and hence the nucleus of nitrogen is able to pull that outer shell in a little bit tighter. You see where this is going. The more electrons we have on that outer shell as we add them with oxygen and fluorine and neon, basically the more places there are for the nucleus to grab onto that outer shell and pull it in just a little bit tighter. So this means that indeed, even though we're adding electrons, but we're not adding any new shells, as we add protons, the nucleus is able to exert a stronger grip on the outer shell and pull it closer. Hence, as we go across a period, atomic radius tends to decrease. That means if I asked you between calcium, gallium, and selenium, which would you expect to have the smallest atomic radius, you, being the smart critter that you are, would of course say selenium, because it's the furthest to the right on the periodic table, and therefore it would have the smallest radius. What about rubidium, silver, and tin, Rb, Ag, and Sn? Which one of these would you expect to have the largest radius? And again, you being the clever critter that you are, would say, well, rubidium, of course. It's farthest left in its period, and therefore it will have the largest radius, because there's only 1 electron on that upper shell, and therefore there just aren't a whole lot of places for the nucleus to get a grip. Wow, you're really smart, you know that?